Hello and welcome to Lars's Electric Endeavors. In this video we are going to be cleaning up the AI slop that we made for this project in the last couple of videos. And we will be using our human brain to write some sensible functions for controlling this servo and the other features on the board that we need. And then we will also be cleaning up the test cases running in the interactive test suite to make them more concise and effective instead of the slop that we have now. And after the cleanup, I want to implement some main application logic also in this project. And my idea is that we have this blue button, and when you push it and hold it, I want the servo to turn clockwise. And if you don't push it, if you don't hold it, but you just push it and tap it, I want it to turn counterclockwise. And that should be a suitable task for this video to finish that. And then I will provide a download link for the state of the software when all of that is said and done, so you can get your hands on the software if you're interested. So let's get started here. First, I will show a demonstration of the state the project is in by going through the test cases we have. If we restart this, you see how this test case goes through these movements here. I don't really like the test because I think it's better that you have some interactivity where you can manually try and move the servo and verify manually that it does what you want it to do. So this test case probably has to go and be re-implemented. Then we have the LED blinker. It's fine. There's no need to change that. Then there is the button test. Yeah, I don't really love it. It's too verbose and too clunky. We will make it in a much simpler way if you stick with us in this video. Then there is the test case where we are dealing directly with the PWM generation. And we can just try it now. I can start the PWM. I can give it some different presets. And I can single step the value here with plus and minus. This test case is totally fine. I like the interactivity. Then there is a demonstration test case from the Freedom Kit and another one. These demonstration tests, let's get rid of them. We don't need them anymore. So let's get started here. For this task, we don't really need the chat that much here, so I'm gonna just hide it. But we will be needing the cursor tab complete. And when you use that, in my experience, it's very, very useful to have a shortcut in here for toggling the tab complete on and off. And I usually put it as Alt-T. Sometimes it's, for my mental sanity, I feel like it's very important to turn it off and just write your own thoughts without constant distractions. So why don't we take a look at the test cases here as they are now. We have the LED blinker, it's fine. Then we have the button test. Yeah, let's do that a lot simpler here. Press, push the button and observe if the correct state is reported. Exactly. That's really all we want to do in this test case. End test. Let's implement that. So our main while should not wait for the button. The while here should be similar to in the other test cases, where we are waiting for space. We are receiving a key from the serial port, and if the user pushed space, we will end the while. If they hit escape, we will show the usage help again. That's totally okay here. But it's button. And then we will keep the state. And we will say new state. And we will check if the state changed, exactly like cursor suggested. And we will print the new state. Perfect. And this test case always returns neutral, which is fine. We can get rid of all of this. I think that should be okay for testing. I'll just move the button to the top here, so it will be the first test case. Build, test, and program. Yeah. That's all we need for that. Beautiful. So here we have our PWM test. And what I want to do now, I want to visit the functions in the HAL layer, the hardware abstraction layer. Just review if we are happy with these functions. Because there is a function for starting and for stopping the PWM control, which is the control signal for the servo. And then there is a function for setting the duty cycle in percentage. The problem is, this is an integer between 0 and 100. And the effective usable range for this servo is only from 3 to 11. So that only gives us like a handful of steps actually. So the control right now is very coarse of the angle of the servo. And that's really stupid because we have a very, very accurate timer. We can do much better than that. And what I want to do here is to simply use float. Oops. For specifying the percentage so we can have decimals. And just like that, that's fine. And the float can be negative, and let's do a proper range clamping here. And then we want to make the calculation in float here. So I will read the maximum value of the timer, the reload value, in float. We will make a multiplication here in floating point and divide by 100 in floating point. And when that is said and done, we convert to integer. I think that should be fine. Actually, why don't we multiply by... I'm not sure if that really makes a difference. It just looks better in my eyes to make a multiplication instead of a division. Okay. Now that we changed this function here, we need to change it also in the H file. And then it's a very good time now to revisit the PWM test case and adapt that to use floating point. Yeah, and cursor is being helpful here. Yeah, so this looks correct, and it is correct, but there is a problem now. I tested this code previously. So we are using a limited version of the standard library for an embedded target like this. And in this case, the library actually doesn't support to do format printing for floating point numbers. So this will not work for our platform at this point. I'm sure there is a compile flag we could toggle and enable the floating point here. But I propose that we simply convert to integer and just print it as an int. It will be fine. Yeah. What happened? I always get nervous when something quickly changes here because sometimes when you do the tab complete in the cursor, it decides to delete a bunch of stuff. as the tab complete action. I guess we could do rounded conversion here. That's maybe even more correct. Okay, let's see if that works. So this is the PWM test. Let's move that to top and see if it works. Start. 5, 10, and we step. It works perfectly fine. So this is a nice process when you're writing code here. First you modify your functions, then you modify your test case, and then you verify that things are working the way you want. So the next step is the servo, higher level logic control of the servo. And right now we have a function now inside of the HAL module called servo control. I want to move it to a separate code module in a driver folder. I want to make a real driver for the servo control and not just have a HAL function. So the hardware abstraction layer, the way I like to build software, this should be only an abstraction of the lowest level functionality in the microcontroller, while something like a servo to me is something you connect to your board, and it's kind of like the next level in the stack of your software. I like to make a driver for that. No, that's not the intention here. Drivers is the folder name, and then we make something called servo here, and this is a C module. So that's why I make a C and an H file. And here I want to use I need my template for generating the boilerplate code here. This is too empty. And I prepared the template here. So this template I always use in Cursor here, and it fits in here. So now I added this templates file, and it has two templates inside of it. There's the H file template, and then there's the C file template. And they contain all the boilerplate code, including some variable substitution magic going on here. And the end result is that when you make a new file, I can use control space, template, write template, and then I pick the template from here, from the drop down. And now I will ask Cursor to shut up. And then you get your new file with the perfect decoration here, where you have a file name, we have the current date, you have an include guard that you always need in C, where you have the folder name, you have the file name. And for the C file, there is a similar substitution going on here, where we have the H file already included corresponding to the file name. We have the C file, and it just makes it very easy and fast to make new code modules. And this is what we will be using here. So the servo control, let's call it like this instead: servo set position. And then I want to specify a value here. And I feel like it makes sense to just use 0 to 1. Position 0 is fully counter clockwise. Position 1 yeah, I feel like that's the sensible API for this. Stop PWM. I also want to have a function for turning off the PWM signal, in case you want to give the servo a break. Okay. And let's implement that. Maybe Cursor can help us now. We need the HAL module here. Yes, like that. So we have squiggly lines here, and this is because the IntelliSense is looking in this folder here. We have the CLangD language server for the IntelliSense, and it's looking in the build debug folder. And right now, it doesn't really, it cannot find the files for compiling this file. So we need to make a build. Let's just build the app, debug. And I think that should solve the problem. Oh shit. Now it's better. Now it understands the include. And now we have this one. This is correct. We need to maintain a variable, a boolean to keep to remember if we turned on or turned off the PWM. So I want to make a static bool here. PWM on. And here we turn it off. And here, if it's not on, then we turn on the PWM. Yes. Then I also want to have some defines for the minimum and maximum position of the duty cycle for the two extremes of the servo. I believe it was 12, wasn't it? So now we can, in floating point, we can calculate the position times the range, and then add the minimum duty cycle. That should be fine. And then we set it here. But of course, this should be done before turning on the PWM in case the PWM is off. Then we want to set first the intended value and then turn it on to avoid a glitch. So I think this looks correct. And it compiles. So it's time to update the test case for this. Usage servo control. I don't like this test case at all, the way it's done here. Let's do it in a different way. Well, we can keep the same name. Why don't we use AI actually to write this test case? I'll just get rid of it. Because we have a very clean interface here. And it's very obvious what's going to happen in the test case. So I feel like we have good chance for AI to help us out here. Please write a test case for the servo driver. There should be a way to set fixed duty positions. Key 0 is corresponding to 0. No, let's do like this. Key 1 corresponding to position 0 and key 9 to position 1.0 with the keys in between for equally spaced. Add key O should stop the PWM. Key S should start it. Let's make a start stop here. It's better. Then we don't need to deal with the This will be a simple wrapper of the hell. It's better than maintaining a state in here. Yeah, let's do like that. Okay. Yeah, that's fine. I believe AI should be able to implement this just fine. I'll pause the video and then come back to you when the agent is done. Okay, so the agent wrote a test case for us, and it ran the build script test that it compiled. So what did it do? Let's just keep everything. We can set the position and we can start and stop the PWM. Yes, this is exactly what I was expecting here. We pick up the numbers from the terminal, the number values you can enter, and then there are actually 8 spaces here. But it's using, yeah, that's not nice. Let's do like this. See, so now I want to print first the whole number and then 1 decimal where we have the oops. Please convert C to whole number and decimal 1 decimal, and use that for the printf. This is again the problem I was talking about before, where, yeah, exactly this, where we don't have the floating point printing. And here what we are doing now is we are printing the whole number and then 1 decimal calculated manually. Let's see if that works. Hell servo control. Let's run that first here. Program. So maybe you're wondering why I use release for program. There is no particular reason. It's just because the code is more efficient and we are not using any debugging tools at this time. We are not single-stepping the code. We are not inspecting the variables. So we don't really need the debug symbols and the debug aspect of the way you compile it for debug, where you turn off the optimizations. We might as well use the release. But both will work actually. Let's reset. Yeah. Which does not work. Interesting. Our test case is not working. What did you do? Yeah, it's getting late here. The problem is I was not building the test case, I was building the app. There we go. Okay, servo control. Let's put 5 here and start the PWM. So this is the center position. Maybe we can actually move this. Yeah. This is approximately center. And then 1. Ah, okay. This works perfectly, except that I wanted the low number to be all the way over here and not over here. But this is exactly how I expected this test module to work, except that we actually have the rotation incorrect. This is not a fault of the test case, this is a fault of our server module here. So this should go in the opposite direction. Please reverse the math so is is reversed. Yeah, fix it. Yeah, that's right. Start PWM. One, that did not work. Why didn't it work? Because I didn't save the file. Let's try again. Start server PWM. One, all the way to the left, and all the way to the right. Beautiful. I'm happy with that. We have this. Then we have the demonstration tests. Let's get rid of them. There. Does it compile? Yes. I feel like this is a good time for committing some stuff here. Yeah, I'll just add the templates here. Okay. Servo module. Added servo module. Cleaned up test cases. Goody good. And now it's time to implement the main application logic I was talking about in the introduction. And where does that logic go? It's in our main.c when we are not running the test case, interactive test. Then we are running the start application function instead for this code here, this part of the code which is intended to implement the main application logic. In bigger projects, I would have a folder here called app, which will be like the top level of the software stack, where you have all the high level logic going on here. But in this case, we're not going to bother with that because it's only one function here. And what I wanted to implement was this feature where if you hold down the button, we turn to the right, but if you tap it, we turn to the left. And in order to implement that, I want to, let's do like this, turn off the tab. We will make a function here, a helper function. Read state of button and return number of ticks it has been depressed. Yeah, this is so simple. Check button. Maybe tab can help us. T. And let's keep a variable here. Button ticks. Yeah, namely. Exactly. And now here, I want to start at 0. Now we check the button here. And we want this loop to run at a limited pace. If we sleep 10 milliseconds, it will run with 100 times per second here. If ticks is higher than, let's say, yes, 10, so that's like a tenth of a second. 50, that's half a second. Let's take 20 here. So if we are holding down the button for more than 20 ticks, then we are holding the button down and we will turn in a positive direction with the servo. Start in the middle here. And we increment the position. Let's do it a little bit faster than that. And if we reach the limit, we should just stay at the limit. So let's do like this. If ticks are not above 20, let's store the old ticks. if ticks are, we're already here, so it means that we are already in a case, in a branch where ticks are not higher than 20. If old ticks is more than 0, and if we store the old ticks here, that means we actually did press the button, but it was less than 20. So if we are tapping the button, we will end up in here. And then we subtract. But we only do it if we are more than 0. And then we set the position. And here we make sure that the servo is turned on. So we need to include the servo module. I'm not 100% sure that this logic is correct, but let's just see what happens. It works. Ish. It moves too fast. Let's do like this. Yep, it works. Why does it go to the left first? Yeah, it's because of the way the code is written. Wait a second. Yeah, the problem is we need to check that ticks here is 0. We will only get into this branch when we are not pushing the button. And then we check if we previously did push the button, and then we decrement the position. Let's see if that's better. Yeah, it works. Except that the backwards, this is not really, it would be nice if it was a bit more responsive when you go in the other direction. Of course, I could make this number larger. I think this will have to do for this video. Let's see what happens here. 3. Ideally, yeah. Ideally, this should be made in a more clever way. But the point of these videos is not to implement some super fancy mathematics logic here. The point of these videos is to show you how to implement code on an embedded target using AI in an effective way with a test suite. So we will leave it at that, the way that the code is here, and I will end the video here, and I will make sure that there is a download link where you can get hold of all of this here, including the cursor skills we made, and including the templates here. But please change the name if you're going to use the template. Otherwise, just take it. Of course, everything here is free to use. So thanks for watching, and see you in a future video.